Still getting the hang of this Zoom thing. It's I'm getting there though. So there's a few questions up posted. You guys can see that, right? Perfect. Pop quiz, huh? That would suck, wouldn't it? First thing Monday morning, pop quiz. All right, you guys want to get started? Let's get started. We've got a bunch of people on now. Let's start chatting. So we're going to talk about temperature and relative humidity, or sorry, temperature and humidity today, and what that means to the greenhouse environment. We'll get to the settings and all that stuff, I think, next week. But today we're just going to talk about the, I guess, the theoretical stuff behind temperature and humidity and how that affects the crop and the greenhouse climate. This is going to be review, I hope, but it's going to be hammered home. I'd like for you guys to know this before you leave. This is important to crops in general, right? So temperature and humidity are vital to understanding what's happening in the greenhouse and what's happening within your crops. So have a look at this first question here. The greenhouse relative humidity is 40% with a temperature of 20 degrees Celsius. The outside relative humidity is 80% with a temperature of 5 degrees Celsius. When we open the vents, will the air dry out? What do you guys think? I don't know if you want to write in the chat. Tell me what you guys think. Will the air dry out? Yes or no? You guys can just write no, yes, whatever you want. Jesus Christ, sorry. I think it's the Starbucks coffee. Whatever cream they use, I don't know. It just gets jammed in my throat. Cream's bad for you.
Matt, I have a question.
Yes, please.
It may be silly. What do you mean when you ask, will the air dry out?
Okay. Yeah, that's a good question. Will the humidity in the air leave? Will it drop below 80% relative humidity?
Okay.
What do you think? So Chad says no, the air will not dry out. That temperature difference on Devon. Angela agrees with Devon. How often does that happen, Devon? What do you guys think? There's got to be more than 3 of you that have an opinion. I'm curious.
I think it's going to dry out.
Yeah?
Yeah. I think all the humidity and hot air is going to rise out.
Okay. Yeah, just based on feel, right?
Yeah.
Okay. Temps may be higher, so is the humidity. It'll likely be an exchange, sort of. Okay. I think no. Well, a lot of you say no, right? You think it will dry out. So there's a mix. It's only 50%. You got 50% chance to have it right. I'm just going through your chats and giving you time. Higher humidity outside. Okay. All right, good. So this is a good response. I like that. This is good discussion. So some of you saying, so Corey talked, he's saying that there's a warm air in the greenhouse and the humidity will rise up with that temperature, leave the greenhouse. But what's it being replaced with, right? What do you think? It's 80% outside. Do you think that 80% is going to come into the greenhouse? what does that mean? You know, what does relative humidity mean? What does 80% relative humidity mean? Do you guys remember that from last term?
It's also relative to the temperature of your greenhouse.
Yeah, you got that, right? It's relative humidity is a ratio, right? Relative humidity is a percentage of moisture that's in the air. But that percentage is going to change along with the temperatures in the air, right? There's going to be different terms that I'm going to throw out at you. And I'm going to give you guys these questions to kind of go over and kind of think about as we go. And I'm going to give you time to do it. First exercise, I've got, bear with me for a second. Why doesn't my thing pop up? All right. I got a couple windows open here. Let me just figure all this stuff out. I'm going to give you a table. And these are just given, okay? These are given terms, given numbers. There you go. So what we've got here is the beginning of a table with temperature and grams of water in the air per kilogram of air. All right. So there's a lot of physics involved, and we're not going to get into a deep discussion on physics and stuff first thing Monday morning, but this is going to be a little heavy for a Monday morning. So sorry about that. You know, if we, the air is going to hold so much moisture, okay? And we have a meter cubed of air. We know what that weighs, right? Physicists, scientists figured that out. Much more intelligent people than myself have figured all this out. But we can figure out how much moisture is in the air based on the air volume of our greenhouse. Okay, we'll take the NC teaching greenhouse for instance. Right, we've got an average gutter height. Well, let's say 5 meters. All right, for every 1 meter square of cubed of air weighs about 1.2 kilograms. Right, we know that our gutter height is 5 meters. We can figure out how much a column of air weighs over 1 meter squared. You're not going to be tested on this, so just bear with me, okay? We know at a given temperature, there's so much moisture in the air, right? So if we look at this table, for instance, most of our greenhouse temperatures hover around the 20-degree mark, right? So at 20 degrees, there is 15 grams of air per kilogram, 15 grams of moisture per kilogram of air. Okay, we know that. From there, you can figure out a whole bunch of different conditions within the greenhouse. We know we can discuss relative humidity. We can discuss absolute humidity. Absolute humidity is the actual.
Hey, Matt?
Yep.
Can you just confirm whether you said, I thought you said 1 meter cubed, but then I thought you said 1 meter squared.
Yeah, so a meter cubed is the volume of air within that water.
Oh, okay.
The greenhouse, right? So if we extrapolate that, put that to a column, we can figure out there's a whole like pressure on the crop, the amount of moisture within the air within that column. But then I said square metered, so I'm talking about that column is going to be a square meter in area.
Gotcha. Sorry, thank you.
No, please clarify. If you have that question, I'm sure a lot of others do.
Thanks.
Right, so there's a few terms and definitions that I'm going to expect that you know, and we'll review them right now. Okay, so absolute humidity, we're going to talk about saturated moisture content. We're going to talk about relative humidity. We're going to talk about VPD, vapor pressure. We're going to talk about humidity deficits. So all these terms are going to be thrown around, okay? And with knowing this little bit of information, we can figure out all of those things with some math. Math and graphs. Okay, so I'm going to give you guys what's called a psychrometric graph or the Moliere diagram. We're going to go over that. Okay, so let's talk about this question here. What I want you guys to do, because we're going to get into graphs, I want you guys to graph that. Okay, I'm going to give you guys a few minutes, and I want you to plot this graph. So you're given temperature, and you're given moisture content in the air at that given temperature. These numbers are going to vary, right, based on where you are in the world. But this is relative to kind of where we are with the pressure that's like above sea level. So the altitude that we're at, this is what our conditions would be. Okay, so and it's all relative, right? So what I want you guys to do is plot these numbers on a graph. Okay, so I'll give you guys a few minutes to do so. Just reading some of your comments. Sav, you're going to create this table.
How's this look, Matt?
Wait. What do you got? Yeah. Oops.
Hey, thanks. Needed the confirmation.
What do we think? Most of your graphs look like Macy's graph there.
It can't be worse than Macy's graph.
Come on. You can do it a couple different ways, right? I didn't tell you what the x-axis or the y-axis is going to be, but it's going to be relatively similar, right? So there's, I mean, you could put the temperature of the y-axis and the.
So can I ask you, Matt, like, why did you choose degrees at the bottom? I chose degrees going up because the last graph I remember seeing, we had degrees up the side.
I did it because this is going to be different than what I'm going to show you. Just to show a little difference, right?
Okay.
Psychrometric graphs in general, that's what they're called in Canada and the US, in any English-speaking area. You're going to have temperature on the bottom, and actually there's going to be grams per kilogram, grams of moisture per kilogram of air on the right-hand side. And the graph is going to look like that. But I'm going to show you something today. It's called the Molier Diagram, and it's those Germans that developed it. If there's anything wrong with Germans, sorry. There's more information on the Molier Diagram than there are on psychrometric graphs that you're going to find on the web. So from here, so you plotted this graph and probably looks something similar to this. What I want you guys to do from here, so this is the amount of moisture that could be in the air at this given temperature, okay? Doesn't necessarily it means that it is, right? If we had 5 grams of moisture per kilogram of air at 5 degrees, what is the relative humidity at that point? Would you all agree that that would be 100% humidity? You got it. Some of you are saying 100%. You got that. Now, more math. What I want you guys to do, so if this is 100%, I want you to fill in the rest of the table from 100 to, well, 0 is going to be 0, to 10%, and go by tens. Okay? I'm going to give you guys another 5 minutes to do that. So finish this table here, and you can then graph it if you'd like. So extend this table out to have 90, 80, 70, 60, 50, 40, 30, 10% relative humidity. And what do those numbers look like? Okay, I'm going to give you 5 minutes to do that while I get rid of some of my coffee. Start talking with the mic muted. Are you guys making out? All good? So what do we have? There. Your table look like that? Maybe?
Not even close.
Come on.
Same with, oh no.
Oh.
And 5 minutes if you did, bravo.
So simple math, a simple equation. This is 100%. If we want 90% of it, multiply this number by 0.9.
Oh, I am, yeah, I'm with you now.
0.8, 0.7, all the way down, right? So, hang on, let me. Share this. You see that whiteboard or no?
Mm-hmm.
Yeah, so I can do. You see my scribble?
Gotcha.
Okay. Bear with me. I'm trying to draw with my mouse. So we have 5 over 5 equals 100%, right? That's awesome. I feel like I'm in kindergarten, right? So we want to know what x over 5 equals 90%, right? So 90% is what? 90% is 90 over 100, right? So then we cross multiply, all that fun stuff, and you solve for x. So x is going to end up being 5 times 0.9, okay? So 5 times 0.9, okay? And then that'll give you your number, what is it, 4.5. All right, so there's your simple little math lesson. Formulas. Well, it's good practice, Sav. Sav's doing some formulas on Excel that he'll share with everybody after. Oops. There you go. So let's go back to the question. Okay, so I'm sharing my document again, right? Just nod you. Corey and Erica are on video. If you nod your head, I'm golden. Corey, can you see this? Perfect, thank you. So go back to the question. So if the greenhouse has a relative humidity of 40%, temperature of 20 degrees, outside relative humidity is 80% at 5 degrees. Will we dry the greenhouse out? Will we have a drier environment, so a lower relative humidity when we exchange that air? So there's going to be some variables that that you guys don't know, like what is the exchange rate, how big are the vents, all that fun stuff, right? Like, are we exchanging 1-to-1, one part of air outside to one part of air inside? There's a lot of variables. So we're just assuming that we're going to exchange 1-to-1. So one part of air goes out, another part comes in. Okay, so let's look at the conditions, right? So if we have 20 degrees, how much moisture is in the air? We have 6 grams of water per kilogram of air. Okay, so for every kilogram of air that exits the greenhouse, 6 grams of moisture is going to exit. Outside is 5 degrees, and we have a 40% relative humidity. Two grams of moisture per kilogram of air is going to enter the greenhouse? Oh, 80%. Thanks, Santiago. Still, 80% relative humidity outside, 5 degrees inside. So that means 4 grams of moisture is going to enter the greenhouse per kilogram of air. 6 grams out, 4 grams in. We have less moisture coming into the greenhouse than leaving it, right? So our greenhouse air is in fact going to dry out, right? So you can make those assumptions based on what you see, but you kind of have to go look at the numbers, right? You have to know what's going on before you can just jump to those conclusions. 80% relative humidity outside seems high, okay? But the air is cold, therefore it can't hold as much moisture as warmer air, okay? So relative humidity is the amount of moisture in the air relative to the temperature, okay? So it's a percentage or a ratio. It's a percentage of moisture in the air at that given temperature, okay? So we know, because this graph tells us how much moisture is in the air at given temperatures, okay? Our sensors tell us what the temperatures are in the greenhouse, and this is how they get the relative humidity based on what the temperatures are in the greenhouse. Does that make sense? All right. Won't the greenhouse temperatures drop? Yep, it will. So again, if we're not exchanging all of the air out and in, but we are having the moisture leave, right? So the greenhouse temperature isn't going to drop down to 5 degrees. It'll drop down a couple degrees, and we can measure that, right? So it might not be exactly a 2 grams of moisture per kilogram of air difference, but it will dry out. So that's a good question, Cam. This is just showing exactly what's going on, right? Yep.
Can you hear me right now?
Yeah, go ahead, Dev.
Okay. I'm just wondering if there's like any type of like rule that we can use, or should we always have like the graph out when we're going to try to be analyzing something like this? Like, are we going to always be like, if it was like, let's just say a question like this, let's say we know it's like 25 or 20 in the greenhouse, and then it's only 5 or 6 degrees outside. Do we always know it's going to drop, or is it kind of like something that we should always be double checking?
Yeah, you can make that assumption, Devin. It's a pretty good assumption. That's a good question. So if it's cold outside, you're going to know that there's not a lot of moisture in the air, right? The warmer the temperature, the more moisture it's going to hold. The colder the temperature, the less moisture it's going to hold. That's always going to be true, 100% of the time. That's why we can have, we can dehumidify a greenhouse very well in the winter and not so much in the summer. It's very difficult to dehumidify a greenhouse, especially in the Niagara Peninsula or Southern Ontario in general during the summer months. We usually have high temperatures and subsequently high humidities. So we're exchanging hot, moist air with hot, moist air. You can't really dehumidify a greenhouse in the summertime. In the wintertime, you can do it brilliantly. You can have that relative humidity as low as you want it in the wintertime. You guys all have, I'm sure, have experienced dry, chapped skin, chapped lips. You know, you touch a doorknob and you get static, you get a shock in the wintertime. Right now, I'm sure I know my hands are dry, not only from the rubbing alcohol that we have to put on, but because there's no moisture in the air. When we heat up our house, all that humidity that's in the house, our relative humidity gets lower, right? Because the outside air is actually really cold and dry. And anytime we open the door or open a window, we're exchanging all of that moisture with dryness. So our bodies dry out. That's why we experience dryness in the wintertime. So from here, what I want to share with you guys is we're going to go through these questions, but I want you guys to have the Moliere diagram with you, okay? Man, I'm sorry. Bear with me. There we go. So I'm going to share the Moliere diagram. We're going to go open this. I'm going to stop sharing this. Lower that for a second. I'm going to open some tab. There it is. Where are we? There we are. Share screen. All right, Moliere diagram. So here's some definitions on this as well. Okay, so relative humidity is the amount of moisture in the air relative to the how much the air can hold. So temperature. Okay, so here's some. You guys can see that, right? This is stop sharing. I'm sharing the PowerPoint here. Okay. Yell at me if I'm not, and I'm not making much sense.
I see relative humidity and saturation.
Yep, perfect. Thank you, Corey. I'm relying on you to tell me because you're on the top of my screen right now with your cool backgrounds.
No problem.
So yeah, here's some graphics to kind of explain that, right? So we have temperature, the greater the temperature, the more the moisture can hold. So this yellow ball represents air and air temperature, okay? So the colder the air, the smaller the quote unquote the air molecule. Not necessarily true, but the slower the air molecules will move in the atmosphere, right? In the environment. Therefore, there's less space between the air particles or molecules to hold the water. As the air increases in temperature, the ability for the air to hold moisture increases. This messy looking thing is called a Moliere diagram. This is a psychrometric graph that's completely upside down from what you just made, right? So we have temperature going up the left-hand y-axis here. We have absolute humidity, so grams per kilogram of moisture in the air. So Macy, this is what your graph would have looked like with your moisture on the bottom. And we have a whole bunch of other stuff around that we'll explain as I go, okay? So the very first column that you guys created, or I gave you, was 100% relative humidity. That is it's what's called the saturated moisture content of the air. That is the amount of moisture the air can hold at that given temperature at 100% relative humidity, okay? And that is going to be this bottom curve of the Moliere diagram, okay? So this is 100% relative humidity. The number is going up the side here and across the top. That is percent saturation or percent relative humidity within this given temperature. Following me so far? Good. If you're not, yell at me, please. So at 100%, like I said, we can figure out at any point what the temperature is and what given relative humidity that states, just following the graph, okay? So if we know that, for instance, what's the relative humidity at 22 degrees? We go 1, 2, and then we come across all the way over. We can figure out what the relative humidity is based on these curves, okay? So that table that you created The rest of it, so from 10 all the way to 100, are these numbers here. Okay, so this is 100%, and then going up and following down the curve, 90, 80, all the way down to 0. Okay, so finding the relative humidity, you just need a couple points of the on this graph. Okay. Calculating the relative humidity on the Moliere diagram, we have the dry bulb temperature. So now we're looking at the sensors within the greenhouse, the bird box. Okay, the dry bulb and the wet bulb temperature. Right? We know what that is from the last couple of weeks. Dry bulb temperature doesn't have the wick on it. The wet bulb temperature is measuring the evaporative cooling in the greenhouse. Okay, so the dry bulb temperature is 20 degrees. The wet bulb temperature is, so we're going to find 20 degrees on the map there, follow it over until we hit 15, and we're going to go up. This arrow should be pointing up. Okay, so we're going to follow 15, so the wet bulb temperature, and we're going to follow that all the way up to the percentage of relative humidity, which is between 50 and 60% relative humidity. Okay. The wet bulb temperature is this 100% saturation curve. Okay. And that arrow we're going to follow at 15 degrees because that's what we're given. So 15 degrees. We're going to follow that diagonally up. And then we're going to hit the 20 degrees, and that cross section there is going to give us our relative humidity. Okay. I'll share this Moliere diagram. I haven't done that yet. Just follow along for now, and I'll share it, and you guys can have it, a copy of it. So in this case, relative humidity is approximately 56%. Absolute humidity. What is absolute humidity? It's the actual amount of moisture in the air. Okay, so water in the air in grams. It's measured in grams per kilogram of grams of water per kilograms of air. And these sponges indicate the air at a given temperature. Okay, so the absolute humidity doesn't change, but the amount of water the air can hold changes as our temperature increases or decreases. Subsequently, our relative humidity will change as our air temperature changes. Okay. So you see, this absolute humidity is the actual amount of moisture in the air. We calculate the absolute humidity. We'll look at our trusty Moliere diagram, and we know, given in the greenhouse, that it's 20 degrees with 75% relative humidity. We can find that that absolute humidity. Let's find our 20 degrees. Okay, and we're going to find our 75% relative humidity. We're going to travel all the way down until we hit that 20 degree mark. Okay, and then we're going to travel down straight down to find our absolute humidity down here. Okay, so that's 11 grams of water per kilogram of air. Okay. The saturated moisture content, or the wet bulb temperature, or 100% relative humidity, is the maximum amount of water the air can hold at a specific temperature. Okay, so finding our saturated moisture content at 75% relative humidity. Travel up, let's find our 20 degrees. Okay. 75% relative humidity. We're going to find that cross section, and we're going to come straight across. Okay. So our saturated moisture content, because we're coming at 100% relative humidity, right? We're going to find that cross section at 100%.
Sorry, Matt.
Yep.
sorry, Dan, if this is a silly question, but the first thing you're always going to start with the air temp.
We're gonna start with whatever's given to us.
Okay, because okay.
The temperature is so I'm gonna start with my air temperature.
Okay.
And then we're gonna and then I'm gonna follow down relative humidity, and we're gonna find that cross section. We're gonna extend it all the way over to 100% relative humidity or saturated moisture content, and we're trying to find the amount of moisture in the air. So we're gonna bring it all the way down to the grams of water per kilogram of air. We're at 15. Okay, the actual number is like 14.7 or 14.6, but we're going to round up because they're easier numbers to work with. Humidity deficit. It's the difference between saturated moisture content and absolute humidity. Anytime you see deficit, it's going to be a difference, right? We're going to have a difference of the amounts. It's the amount of water that the air can still absorb. Okay, so this is a good measure of possibly like transpiration. Okay, so how much more moisture can the air hold at a given temperature? This is a good indication of how much more water the plants can add into the air, right? So humidity deficit along with something like vapor pressure deficit will give us the amount of transpiration that can happen in a plant. And I've got a bunch of questions that or scenarios to follow that are gonna follow this term here. How much more moisture can the air actually hold? Okay, so let's find that out on the Moliere diagram here. So we know the air temperature is 20 degrees Celsius. The relative humidity is 75%. Okay, so we can find the amount of moisture that's in the air at that given with those given numbers. Okay, so the amount of air is actually in the greenhouse is 11 grams per kilogram of air, 11 grams of water per kilogram of air. And we know that the amount of moisture the air can actually hold is 15 grams of water per kilogram of air. We're going to find the difference between the two by subtracting those two numbers, and we can end up with 5 grams more of moisture per kilogram of air. We can add 5 more grams of water per kilogram of air if it was 10, but it's 11. Monday morning, I apologize. So it's at 20 degrees, 75%, it's 11. Sorry, I just saw the 10. So we can add 4 more grams of water per kilogram of air. Sorry if I messed you guys up. So 15 minus 11 is 4. We can add 4 grams of water into the air. Okay. So that can tell us the transpiration rate, right? It can give us a good indication of a transpiration rate of the plants in the greenhouse environment. Cool. All right. So why don't we, before we get into dew point, why don't we go over some of those questions again to kind of hammer this in? I'm going to open up this document again. We're going to share. You guys can see this question. So the greenhouse is set to 20 degrees with a relative humidity of 80%. The sun comes out and the temperature increases to 27 degrees Celsius. Will the plants transpire more? Or why not? So we can use the Moliere diagram for that for sure, or we can use this chart, right? Either way, we can figure out the amount of moisture that's actually in the air and how much more moisture the air can actually hold, okay? So if you use the chart here, to come up with that answer, I'm gonna let you work on that for a few minutes just to see. So how can I show the chart? Let's just delete this. There you go. So there's the question along with the chart, okay? So you can figure out how much more moisture the air can actually hold. Will the plants transpire, yes or no? And I know the chart doesn't go up to 27, but you can kind of guesstimate from there, right? Cam says the holding capacity of the air should increase. So we can approximate that, yes, for sure, the plants will transpire more just based off the concept of air temperature increases, the amount of moisture that the air can hold will increase, right? That percentage of the amount of water in the air didn't change. The percentage of relative humidity did. The percentage of relativity would have gone down, right? Based on the temperature going up. So therefore, the amount that the air can hold, the amount of water the air can hold actually increases. So the plants should, in theory, transpire more, right? These would be good quiz questions, eh? We won't have a quiz this Friday, by the way. We're going to wait until we're finished the unit. Now let's look at another scenario. Propagation house has a relative humidity of 98% with a temperature of 20 degrees. How much will the plants transpire? Will they transpire a lot or very little? Why do you say that? Okay, so question 3 here. What do you guys think? You're right, Kerwin. Absolutely. Too much moisture. Okay, so propagation house. So if I'm going to set my propagation house up, it's going to be somewhere around the 18 to 20 degrees mark. And my relative humidity I want set at about 95% relative humidity. You're right. You might think that that relative humidity or the amount of moisture in the air is way too high, and we're going to have disease. Is that what you're thinking, Devin? There's going to be diseases coming with that amount of moisture?
Yeah, that's kind of what I was thinking. I didn't see the first part of the propagation house, but yeah, I think that would kind of be like my general statement about that. If like the relative humidity at like 98 or 99% just sounds like it would be kind of causing problems.
Right? Yeah. Actually, you want, depending on the state of your liners or your plugs, your cuttings or your seeds. So if I get a shipment of cuttings in and I stick them and I put them right on the prop bench, I want my relative humidity as high as I possibly can, right? There's no roots to absorb moisture from the soil. So I don't want the plants, the cuttings to lose any moisture. So I'm going to increase the relative humidity or the amount of moisture that's in the air so the plants will not be able to transpire, right? Their stomates will start to close up, or that gas exchange isn't going to happen. So it locks their moisture in until they start developing roots. Once they develop roots, then we can start reducing that relative humidity down, or that amount of moisture in the air down, right? We want them at that point to absorb moisture from the soil and release it into the atmosphere, right? That's going to start moving nutrients through the plant. Right? There's nothing, that's not happening at that stage. So we want as much moisture in the air as possible. Okay, so propagation. Our propagation house will always be high humidity, and then we're going to move those liners out or plugs out. That's why we tent our cuttings, right? We tent our cuttings to keep that relative humidity high. Okay, so this fourth scenario, again, we can look at humidity deficit to figure out what's happening in each of these greenhouses. Okay, and again, we can use the table to approximate. Just move that up so I can. So greenhouse A has lettuce. It's in that greenhouse. The temperature is 12 degrees with a relative humidity of 80%. Greenhouse B has peppers with a temperature of 21 degrees and a relative humidity of 80% as well. Which crop is transpiring more? And why do you say that? So you can, again, guesstimate based on the table, figure out the humidity deficit, and then figure out from there what crop has the potential to transpire more. And of course, just knowing these two pieces of information isn't going to tell you that the plants are transpiring at a given rate, right? It just gives you the potential of transpiration, okay? So make a prediction based on these figures and then figure it out from the table. Which one would you think? B has a greater temperature, producing greater volumes of water into the air. So you're saying that the plants are transpiring, Chad, so therefore adding more moisture into the air, or has the more potential to do so? Greater transpiration because of the temperatures. Possibly, for sure. Other factors for sure come into that: sunlight levels, CO2 levels, all that fun stuff. Like how much is the plant photosynthesizing comes into transpiration as well. So I guess when I'm asking these questions, I'm going to ask what's the potential for transpiration. So you're going to actually have to go through the exercise to have a look at what that humidity deficit would be to show which one's the greater. Which greenhouse has the greater transpiration potential. So at 21 degrees, let's say at 80%, let's say that for lack of, let's say 13 grams of moisture is in the air, okay? The air can hold somewhere between 15 and 17, so let's say 16, okay? So greenhouse B has the potential for 3 grams of more moisture in the air, right? So let's look at greenhouse A, 12 degrees. Let's just do this. There you go, 12.5. Now we have exact numbers. At 80%, we have 7, we'll round it down to 7, right? And we have the potential for 9. So 9 minus 7 is 2. So you're right, greenhouse B has the greater potential for transpiration. And in fact, it probably is transpiring at a higher rate, right? Because the temperatures are higher, therefore the photosynthesis rate would be higher. But now we know for sure that it has the greater potential. All right, go back to the Moliere diagram. Let's have a look at the dew point. What is dew point? What am I sharing here? This one, I've got so many things open. Here we go. All right, so dew point is the temperature at which water will condense. Okay, so we walk into a greenhouse, usually the third greenhouse, and we have a look in the, especially in the wintertime, we look at the windows. We see on the windows a whole bunch of water forming, condensation on the greenhouse. That's the dew point, right? At what point does at what temperature does that water condense out, right? So if we think about, let's go back a couple slides. This slide here shows it pretty well. So if we have a temperature of 23 degrees and our whatever that volume of water is, as we decrease in temperature, you can see that volume of water doesn't change, but the ability to hold that moisture does, right? So we keep backing up. At 14 degrees is less. At 0 degrees, it's almost there. There's not much potential to hold more moisture. And at -5, look at that. We squeeze that sponge, there's no more moisture coming out, right? So that amount of water doesn't change, right? But now that air pocket decreases to a point where now we're actually overflowing in water, right? And this is the point where dew forms. You're walking out in the morning and you get your feet all wet, or looking at the glass on a greenhouse and the water has a bunch of droplets on it, okay? So that is the dew point. And knowing this is important for growing crops, right? It's important to understand at what temperature the water condenses, because we don't want moisture on the foliage. We don't want moisture on the fruit, right? If we had moisture on a tomato as we pull it and put it in a box, what's going to happen to that tomato once it gets to the grocery store? Right? If we had roses that had dew, and as we're picking them, we throw them in paper to package them up to bring to our customers, what's going to happen to that rose? Right? We're going to have moldy roses and funky tomatoes at the grocery store. I wouldn't be happy receiving that, right? So we should know as growers at what point the water will condense at, okay? So figuring that out with the Moliere diagram, we can definitely do that, right? So we're going to find out what that temperature is, which is 20 degrees. We're going to find that 20 degrees, which is right there. We're going to find 75% relative humidity because we know that. And then from there, we're going to find that cross section, okay? We're going to drop that all the way down to find our wet bulb temperature, okay? And then we're going to pull it all the way back to the degrees Celsius on the side there. So at 20 degrees with 75% relative humidity, our dew point is somewhere around the 15 degrees Celsius mark. So if we drop our temperatures down to 15 degrees, we could have dew forming, okay? Which isn't uncommon in the greenhouse, right? So if we have a look, stop sharing this for a second. This would be much easier in person, but we're making do, right? I think we're doing all right. We have a look at these questions again. And I just threw these down just before class started, so I apologize if there's any grammar mistakes or spelling mistakes on these. I just whipped them together like 20 after 10. So we have placements of sensors throughout the greenhouse, right? The more sensors we have in the greenhouse, the more accurate our readings are going to be, and understanding of what the crop is doing within the given climate, right? Our teaching greenhouse, which is not uncommon in industry whatsoever, has one of those aspirated screens per zone in the middle of a bay. That is not uncommon. Aspirated screen or the bird box, right? We have 2 sensors there measuring dry bulb and wet bulb temperatures, and we're going to get our humidity from there. Our greenhouse, we have multitude of doors. We have zone doors open all the time. So we have different, possibly climatic conditions throughout the greenhouse, right? We know at the sensor, the readings are 20 degrees and 80% relative humidity. What would the conditions be at the back of the greenhouse if we drop to 15 degrees Celsius? Which isn't uncommon, right? Our second zone right now, we have the hydrangeas growing in them. That temperature drops to 12 degrees first thing in the morning, right? What happens when the doors open to those peppers that are right there, right? You think that those temperatures can reach 15 degrees? Probably, right? Our temperatures hover around 20 degrees in the third house, and our relative humidity is rarely 80%, but it can get up to 78, 75%. Will we have dew forming on our peppers? What do you think? Fruit are not producing as many sugars. Foliage will have dew. So Sebastian says there's potential to have dew. For sure, especially in the morning when those temperature changes are drastic, right? So knowing that there's a possibility there, what could we do in that third zone to reduce the potential to have dew forming on the foliage or the fruit? What do you think? Perimeter heating. Okay, so to mitigate the temperature change. Yeah, possibly. So realistic fixes. Yeah, so we would need some, yeah, so we could add some things to protect that for sure, but I'm not gonna spend money at this point in the greenhouse, other than maybe some energy. So Erica says vent out the water. Yeah, so we're gonna purge, eat and burp. You got it. That's purging. And we're gonna go over how to do that next week. We're gonna talk about purge settings. Yes, we're gonna reduce the amount of moisture in the air in that third greenhouse so we don't have water developing on the foliage or fruit. You're absolutely right, right? So if we heat that area up, we warm the greenhouse air that has the potential to hold more moisture now, right? Hot air rises, we open up the vents in the top of the greenhouse. That hot air will escape while it's holding that moisture, and we're gonna bring in some cool, dry air. That cool, dry air is gonna warm up back to 20 degrees in no time, and the air in the third greenhouse will subsequently turn drier, right? Reducing the effect of dew. So I know my staff are coming in at around 8 o'clock, 8:30, somewhere in that general time frame. I know at that point, my staff are going to walk through the greenhouse and have a look at the different crops, opening the doors between the zones. So I will set my humidity reduction settings at around maybe 7:30, 7:45. Okay, we're going to reduce that moisture in that third greenhouse, so we don't have the ability, or so the greenhouse has less of ability to form dew on the foliage or fruit. Okay, that is the strategy that I would use there. The back of the greenhouse, where the doors are and the windows are, there's not really much I can do. There is perimeter heating, and that is set up to increase around the perimeter of the greenhouse. So it is warmer there, but the temperatures do fluctuate, especially when you go up away from the sensors or down towards the ground. So there's a whole bunch of different factors that come into play when we look at temperatures throughout the greenhouse. Okay, so dew point, that's understanding dew point. Question 6 here, we'll get into VPD, vapor pressure, and we'll get into explaining that. Again, this is review, but we're going to talk about it anyway. So setting irrigation will depend on a number of things. We're going to look at perhaps different scenarios as we go through this as well. So temperature and humidity levels are among a number of factors that we will consider when we're setting our irrigation. Right, so greenhouse has a temperature of 20 degrees with a relative humidity of 70%. What happens when the sun comes out and warms the temperature up to 25 degrees Celsius? We can look at HD, we can look at humidity deficit and figure out what the potential is for transpiration. We can also look at what's happening within the plants, right? So vapor pressure and vapor pressure deficit are a direct indication of transpiration rates within the plant itself, right? So if we open up trusty Molier diagram again. So at any given point, at any given time, the air is comprised of a multitude of different things, right? We have oxygen, we have carbon dioxide, we have nitrogen, we got a whole bunch of different gases. All of those gases will exude a pressure at a given altitude. That pressure fluctuates depending on what's in the air. Another contributing factor and a greater contributing factor is water vapor. Water vapor has a pressure that it exudes on the atmosphere as well. And that actually acts independently from all the other air molecules. So we're just going to throw the rest of those air molecules out. We're not going to be concerned with oxygen, carbon dioxide, et cetera. We're only going to be concerned what's happening with the moisture in the air when we're talking about vapor pressure. We can figure out what that vapor pressure is by using our psychrometric graphs. Not even going to get into calculations and physics and all that stuff behind it, because I don't want to. I don't even want to look at that. I don't even want to think about it. So basically, you have to know at a given temperature and relative humidity what that potential of transpiration is based on the vapor pressure. And you can kind of guess with temperature, and relative humidity, what the vapor pressure would be in the air anyway. You have to know what's happening in the plants as well, right? So we can figure out what the vapor pressure is in the air based on 20 degrees and 75% relative humidity. But we have to know what's happening in the plant as well to understand what's happening with the vapor in that plant. Water vapor is always going to travel from an area of high concentration to an area of low concentration. That's what transpiration is, right? So water vapor is going to leave the plant through the stomates and enter the atmosphere if the atmosphere allows it, right? So if the vapor pressure within the atmosphere is lower than the atmosphere within the leaf, we're going to have that gas exchange on a regular basis. And we can predict the speed at which the plant is transpiring based on this vapor pressure deficit between the plant and the air, okay? So in order to find the vapor pressure deficit, we'd have to find the vapor pressure within the plant itself, okay? In order to do that, we need to know the temperature of the leaf. And if you look at our little bird box or our aspirated screen, we have the air temperature of the greenhouse inside that box, and we have the leaf temperature sensor outside that box. That's that green sensor that's dangling off of that bird box. So knowing that temperature of the foliage, we can figure out what the vapor pressure is within the leaf. We assume that the relative humidity within the leaf is always at 100%, always at 100% saturation, okay? So all we need to know from there is the temperature of the leaf to figure out the vapor pressure deficit of the whole leaf versus atmosphere of the greenhouse. Oh, does that make any sense? Do you guys have any question on that ramble I just did? No, you guys all understand vapor pressure and vapor pressure deficit? All right, thanks, Graham. So understanding the vapor pressure in the greenhouse, we'll figure out what the temperature is, which is 20 degrees, it's given. Okay, so at 20 degrees, 75% relative humidity, we're gonna find that intersection, and we're gonna come straight down to this diagonal. Okay, so vapor pressure is measured in kilopascals, okay, along the side here. If we look at the Priva maximizer unit, it's measuring in millibars. There's not much difference. It's a measure of a decimal place. So millibars is, I think it's 0.35. I think it goes that way, pretty sure. And then kilopascals, the decimal place. It's off by 1 decimal place. Okay? Not to confuse you, I'm just going to leave that alone right there. So dropping that down to the diagonal, we're going to come across, and we're going to have somewhere in the range of, what is that, 1, 6, 7, 8, 1.8 kilopascals is the vapor pressure of the greenhouse atmosphere. Okay. So I just did that whole explanation of what's going on with vapor pressure deficit, all that stuff in the leaf. This is posted. I'm not going to go through that again. So what's the deficit? Assuming that we have 100% humidity in the leaf, which is right there, right? At 20 degrees, we're assuming that our leaf is at 20 degrees as well. Okay, so 1.8, and we bring this down from 20. Backwards there. Okay, so 2.4 minus 1.8, we have 0.6 kilopascals vapor pressure deficit. Okay, or 6 millibars of vapor pressure deficit. We can have too much of a vapor pressure deficit. If that happens, that means the air in the greenhouse is super duper dry, and at that point, our plants will start to protect themselves. The stomates will start to close, right? So if our vapor pressure deficit is too much, that doesn't mean our plants are transpiring like crazy. It's going to mean that the plant is going to start protecting itself from wilting, and we are not going to have any air exchange at that point, right? If we have vapor pressure deficit of too little, the air isn't going to be able to hold more moisture, so the plant will not transpire. There's a sweet spot for every crop, and every crop will have a different sweet spot. But in general, if we have a vapor pressure deficit of 0.3 to around 1.1 kilopascals, or 3 millibars to like 11 millibars, we will have some form of transpiration. Okay, and that's not for every plant, but that's a massive range. But anything above 11 millibars or 1.1 kilopascals will be a detriment to the plant. Okay. Wet bulb temperature is saturated moisture content. Before we get into that, is there any questions on vapor pressure deficit? You guys good on that? So if we look at our question there again, what do I need to know from here? I'm not giving you all the information. What else do you need to know in that question to figure out what the vapor pressure deficit would be? What do you think?
Totally guessing the RH, Matt?
We have the RH of 70%. So that's
Oh, I just thought maybe of what
is the relative humidity, Macy, of the plant? What do we assume?
don't know.
100%. So Emily says leaf temperature, 100%. You're right. So we need to know the leaf temperature, right? So we have the greenhouse temperature of 20 degrees and the relative humidity in the greenhouse of 70%. We are assuming, we're making that big assumption in the leaf is 100%. It's a good assumption, right? Unless the plant is completely dry and withered up, you're going to have moisture in that plant. Now we need to know the leaf temperature and we can figure out the vapor pressure of both, and then we can find the deficit. And then finding that deficit will allow us to guess on the transpiration rate. Right? So setting irrigation based on VPD allows us to kind of guess how much more moisture is going to be in the plant is going to add into the atmosphere, right? So knowing what the VPD is, we are getting a better understanding of what the plant is doing, right? With a higher vapor pressure deficit, the plant could be transpiring at a higher rate. There's more to plants transpiring than just VPD, temperature, relative humidity. Sunshine, right, is going to play a big factor in it. Carbon dioxide levels are going to play a big factor into transpiration. But we're making an assumption that all of that is satisfactory and happy. And with a good VPD, we are predicting transpiration in the plant when we set irrigation, right? So what we would do for this irrigation is as soon as the VPD hits a certain deficit, the water will turn on, okay? So with our tomato crop, for instance, if we had our irrigation set on VPD, every time that VPD would hit a certain area or a certain amount, we would hit, the drippers would turn on and the plants would get a hit of water and fertilizer based on our assumption that the plant's transpiring at a high rate, okay?
Would irrigation be the only thing that gets triggered? Would if the VPD gets too extreme, would environmental changes be made as well so that there's not?
Yeah, good question. I do understand what you're trying to say. So we're looking at would we maybe dehumidify if the VPD got too low? VPD is telling us what the plants are doing. We could base our humidity or dehumidifying factors on VPD, but it's not giving us what exactly is happening in the climate, the greenhouse climate. It's telling us what's happening in the plant. In my opinion, I think we should be using relative humidity or humidity deficit or absolute humidity to dehumidify or humidify the greenhouse and change the climate that way. I know some growers use VPD and VPD only, but in my opinion, that's telling us what's happening with the plant versus the environment, not what the environment's happening outside the plant. So good question, Emily. It's definitely one of those topics that are argued amongst growers at times. And actually, I know Hogendorn, before a couple of years ago, they didn't measure humidity in any other way other than VPD. They didn't dehumidify their greenhouses with relative humidity. They used VPD to dehumidify their greenhouses. And in my opinion, that's wrong. I think you should be looking at the climate alone, not what the plant is doing into the plant to change those climate settings. So very good question. Does that answer your question?
Yeah, that makes sense. And so when you're calculating the VPD, you're calculating the pressure, the vapor pressure is like the greenhouse, and then the leaf, and then the deficit is the difference between the two.
You got it. So we're really looking at diffusion rates, right? And diffusion of water vapor, which we call transpiration, right? Diffusion happens all the time. You know Derek's definition of diffusion, right? You ever told you when someone farts in a corner? Someone farts in the corner of a classroom, eventually the other corner is going to smell it, right? So the gas will always travel from an area of high concentration to an area of low concentration. So that's what we get VPD, and we predict. Everybody recalls him saying that. We can predict what's going to happen with that water vapor based on the readings inside the leaf and the readings outside the leaf. That deficit tells us there's an area of lower concentration. Okay, so that's a lot of theory. We can, I think the next slide's on our wet bulb temperature, which we kind of already discussed. We can figure out what the wet bulb temperature is based on relative humidity and dry bulb temperature. Wet bulb temperature is the saturated moisture content, right? And we have those two pieces of information. We can figure out the wet bulb the temperature is 10 degrees. We need to know that temperature, not for growing purposes, but to find out how much moisture is in the air, to find out how much more moisture can be in the air, and to find the dew point, right? So we've already done that exercise, finding the wet bulb temperature. I'm not saying you don't know how to do it, don't need to know how to do it, but that's that. Specific heat content you can find on the Moliere diagram as well. And I'm going to get into this when we talk about evaporative cooling in that unit there. But just to give you a general overview, you can use the Moliere diagram to find that out. So the specific heat content is how much heat the air can hold at a given relative humidity, right? So moisture holds heat pretty efficiently. And again, we're going to get into that at some point later on. But we can find that specific heat content, and that's this 45 to 95 kilojoules per kilogram of air. And that's that diagonal moving up. Okay, so the Moliere diagram holds a lot of information. And that's the end of that. But specific heat content, like I said, we're going to get into it when we talk more about heating and actually cooling of the greenhouse. Okay. So what I'm going to do is share this Moliere diagram. You have this already. You have this PowerPoint, but I'm going to share the actual page with you guys. What I normally do is give you a laminated sheet, but anyway, we're not in class. But it's got its advantages and disadvantages of being in class and not in class. So one disadvantage is you don't have that laminated sheet with, what I would do is you can laminate it, or you can come to me if you're in class, and we can laminate that sheet for you, and you can use your dry erase markers and have a whole bunch of different conditions that you can play around with. If not, just use pencil and play around with the graph. Okay, let me look at my notes here to see if there's anything else that I wanted to chat with you about. Okay, I think that covers it. So if you guys, I'm going to stop sharing this screen and talk to you in person. Do you guys have any questions specifically about air temperature and humidity? No, that's fine. That's good. You will not have a quiz this week. We'll go over the settings. So we're going to talk about temperature settings and humidity settings next week. And then after next week, we'll have a quiz based on all of it. Okay. Do you guys have any questions? If you have any questions about the quiz from last week, shoot me an email. There's still a handful of you that haven't done the quiz yet. And just so everyone's on the same page, there are no late marks for the quiz, okay? Your grade will show up 0 if you do it past the due date. And that's just a way that Blackboard tells me that you guys were late on doing it. So there's no sneaking it in. I have to grade it from there. You're not going to get deducted any marks for writing it late. However, if you stay on topic and you stay on task, it's to your advantage. So I'd still recommend you doing it to the dates specified. Scott, I'm not sure about Derek's classes. You have to ask him specifically. I'm going to make the assumption that he's not going to deduct you guys marks for being late. Unless it's egregious, right?
I have one quick question or comment or whatever.
Yep.
So today we went over like a lot of stuff, and there's a lot of terms, and the only thing I kind of was getting lost on was when we were like had to interpret the Moliere graph. Like, is there like how important for going forward? How important is it for us to be able to like interpret that graph and be able to like line things up and then like pinpoint, you know, like all that kind of stuff like that? How much are we practicing that?
That's a good question, Devin. I would have had you do it more in class, but you're not in class, so I'm not going to have you do specific things with the graph. The graph is there for your reference. Use the graph to understand what's happening in the climate, right? So if we increase the temperature, what's going to happen to the amount of moisture that can be in the air or that is in the air, right? Usually you're given 2 points of information on that graph, and usually it's going to be something like temperature of the greenhouse and relative humidity in the greenhouse, because we have sensors that are telling us that, right? So the interpretation of what's happening in the climate based off of temperature and humidity, we can use that graph to estimate what's going to happen with the plants and what's going to happen with venting and irrigation. Okay, so have a look at it. I'm not going to say study it to its greatest extent, but know how it's used. Okay, look over that PowerPoint again. It'll have the arrows and all that stuff in it as you go. Okay, so you just hit the space bar or move forward, and the arrows are going to come up and show you. And as always, if you have any specific questions, shoot me an email. I'm always available. I'll answer the questions best we get.
Hey, Matt. I was going to ask, how would you compare the Moliere graph to like VPD charts on the internet? Because there's so many, right?
Yeah.
I mean, I've kind of used those in the past, you know, as a point of reference. So how would you compare them? Like, are they alike, or is one better than the other?
No, they're all very similar. They're all the same. The difference will be the accuracy and the units being used, right? So kilopascals or millibars versus other forms of pressure. Greenhouse industry typically uses kilopascals or millibars for your reference. But those are all basically the same. The difference between the Moliere diagram and those psychrometric graphs that measure VPD, the Moliere diagram has all of it in one diagram. Any diagram that I've looked at online, they're all independent, right? So the VPD diagram would be independent to temperature. So using the Moliere diagram, you can actually look at your sensors, your sensor readings within the greenhouse and have it all in one spot.
Okay, thank you.
Okay. You're welcome. There is, here, I'm going to type in this. Let's grow.com. Have a look at that website. That is the website to this plant empowerment textbook that I recommended. And that'll have, if you scroll all the way down to the bottom, there's like a site map. And within that site map, it'll have a psychrometric diagram of different conditions in the greenhouse. What's cool about that one is you can actually change the parameters, and it'll compare from inside to outside, and it'll tell you all of the different answers that you can get. So have a look at that, letsgrow.com, and have a look at the graph there. You can play around with it. Okay. My voice is getting sore. What about your listening ears? I'm sure you guys are bored out of your tears. You guys can go back to bed. I think I'm done. If you guys don't have any questions, Tom Brady equals G. Who is that? Who's going for Tampa? Yeah, Devin, I'd like to go over more scenarios like that, getting back to the class. We'll talk specifically about what's happening in the greenhouse. So I'll give you scenarios, and we'll look at things like graphs and settings within the greenhouse, so it makes sense to you, okay? That's the way I'll teach you from this point forward. We will have to go over the software, because I'm told that I have to go over the software and tell you guys how to use it. One big step. So my big briefcase is actually down in IT right now, and I've got them building me a server. So there's progress, there's movement forward, and I hope to have it tested this week. Have that maximizer unit in the greenhouse, taking measurements, logging data, and have a server hooked up to it that you guys can all eventually log on to and see what's happening in the greenhouse zones, or the zone that it's in. And then you can play around with the software from there, okay? So again, you guys have any questions, shoot me an email, and I'll be happy to answer. Go Bucks go, I guess. Okay. I don't want to see Brady win again. I wanted to see the Bills crush them, honestly. I really did. But alas, my dreams of 25 years were crushed last week. One more ring and he'll be good. Yeah, I'm sure he'll be good now. He's got 6 of them. What do you got to be greedy for? Anyway, on that note, you guys have a fantastic week. I'll see most of you at some point during the week.
Thanks, Matt. Have a good one.
You too. Take care, guys.